Thanks, Sarah, thanks for having me and inviting me over. I really enjoyed meeting and seeing many of you over the last few days. So yeah, thanks for having me. Thanks for the invite. Okay, I'm going to speak about a non-flag arithmetic regularity lemma and counting lemma. So I'm going to take as a starting point or as an axiom that you're at least somewhat interested in sort of understanding averages of these forms. So this particular average is counting 4-term arithmetic progressions weighted by some functions f. So to be clear about my notation, this expectation that I'm taking is just a normalized count over some set. So the set that we're going to be usually counting over is some variables in the first n integers, and I'm going to use the square brackets m to denote that. And my functions fi are going to be one bounded and I guess probably also supported on square brackets n or something. But so that's the notation that we're going to be using. Okay, so a fact that I'm sure you've seen a number of times by now is that the count of 4-term arithmetic progressions weighted by some functions fi is controlled by the U3 norm, the Gauss U3 norm of f1 or f2. So in the sense that yeah, if your Gauss norm goes to 0, then so too does this average. So I'm not going to define the Gauss norms today. I guess mostly because they're still the same as last time you saw them. But yeah, but we'll take this as a black box fact, and yeah, the Gauss norms is sort of just important for motivation and not so important to the body of the talk. Okay. Okay, so to introduce my more general notation, instead of 4 APs, I'm interested in studying arbitrary linear patterns. So yeah, my linear patterns are going to be a sequence of T linear forms, each in D variables. So mapping Z to the D to Z. So in the 4-term arithmetic case, yeah, we put T equals 4, D equals 2, and each of the psi i's, the forms on the slide. Okay, and then I'm going to define the analogous operator, just the normalized count of configurations corresponding to these linear forms weighted by the functions fi. Okay, so the weighting ensures that since the fi's are one bounded, so too is T psi of the fi's. Okay, and then the final fact that I'll tell you is that yeah, so the control of 4 APs by the U3 norm generalizes to control by some Gauss norm of the fi's. And yeah, I mean, so you could ask, or you could certainly be interested in, I guess, so my notation S psi here is the complexity of the system. You could certainly be interested in sort of what the right value S psi is, or I think Freddie spoke in the last week or two about good quantitative bounds in this problem. So doing better than just the qualitative little o notation. But in any case, certainly this is true.
Can I ask you why von Neumann name is attached to this?
So I believe Ben and Terry.
They're the guilty part. Okay. So I don't think von Neumann ever did anything with this, but right. That's okay.
Okay. So
it's an artifact.
What?
It's an artifact, I think. Yeah, the first time this was used, it had something to do with something that has to do with.
Well, I think now that you said, I think Ben and Terry in their progressions and primes, they really mention von Neumann. And von Neumann, we all know it's the ergodic theorem in norm. And whatever you can anything else call it generalized von Neumann. So it feels meaningful. Okay.
So, I mean, statistically, it's if you throw the name von Neumann at a random thing in maths, you might positive probability it might be right. But okay, anyway. So whatever you choose to call this, you get norm control. You get Gauss norm control of these averages. Okay, so now I can state for you what the arithmetic regularity lemma is. So yeah, so I mean, you don't necessarily, if you haven't seen this before, have to pass the sort of quantitative details of the statement of this theorem, but the point is that it's a sort of decomposition result for one bounded functions into a structured part a nil sequence, and a part which has small L2 norm and a part which is suitably uniform in the sense of Gauss norm control. Okay, so how does this feed into understanding the averages that we're interested in? So suppose you want to understand this T psi operator at some sequence of functions f. What you might do is use this decomposition result, write each f as the sum of the three functions specified, and then use linearity in each component in the T operator. And what you're going to end up with is this T operator for nil sequence functions, and then 80 other terms, each of which involves some green function or some red function. Okay, and then loosely speaking, so by Cauchy-Schwarz, anything that involves a green function is going to have size at most epsilon, and then by the generalized von Neumann Gauss norm control, anything which has a uniform function can be controlled by some function of the Gauss norm. And so ultimately, at least qualitatively, you reduce your problem of averaging along these configurations at a function f to an average along evaluated at nil sequences. Okay, so loosely speaking, you can view therefore nil sequences as like extremal or near extremal objects for counts of this form. Okay. And obviously this doesn't only work for 4 APs, this works in generality. Okay, so the arithmetic regularity lemma reduces the problem of studying these general operators to studying these operators evaluated at nil sequences. And so the next goal is to analyze sort of these averages on nil sequences. Okay, so I should probably tell you what nil sequences are. Okay, so I'm sure many of you get so we all know what sort of additive characters are, so a linear phase on the torus. So let me decompose this in a slightly eccentric way. So I'm going to view this linear phase on the torus as a linear sequence which takes values on a simply connected abelian Lie group R. And I'm going to compose that with a smooth function on R, which is automorphic with respect to some co-compact lattice. So my co-compact lattice is Z. The quotient R mod Z is compact. And my function E is automorphic with respect to the action by Z. Okay, this is a slightly eccentric thing to do, but this turns out to be the right definition and the right way to generalize to the broader setting of nil sequences. So I'm gonna, so I replace my abelian Lie group by a two-step nilpotent group. I replace by my lattice by some arbitrary co-compact lattice, and I have a smooth automorphic function. Okay, so I guess technically here you don't necessarily, there should be an extra condition on G2 not lying in the commutator subgroup or something. Otherwise, you might get higher order behavior. But for the sake of this talk, you can just think of a polynomial sequence on a Lie group as just the sequence of coefficients raised to n squared, n cubed, and so forth. Okay, so a good example to bear in mind, which is sort of one step up from the abelian case, is the Heisenberg group. So the set of upper triangular 3x3 matrices and a linear sequence on this group is, well, it's as shown. So the point is that okay, so this is some G1 to the n, and due to the group structure, you get quadratic behavior from a linear sequence, and so so if this was n squared, then you would get some like quartic behavior over here, so it would be considered like a degree 4 nil sequence. But this is the example to bear in mind. Okay, and then when you compose with some automorphic function, the sorts of things that you get out are like a quadratic phase function, which say occurs on, I mean, that's coming from a function from a nil sequence on the torus, or these sort of like bracket quadratics. matrix. So these are the things to bear in mind. Okay, so our goal was to analyze these averages along nil sequences, of these averages of this operator on nil sequences. Okay, so how might one do this? So let's suppose that we have our sort of simplest nil manifold, R quotient by Z. We have some linear phase on the torus and some automorphic function. Okay, so one situation in which is easy to analyze is if is if theta is rational. So if theta is rational, you're going to hit finitely many points in your orbit, and then the average of this function is just going to be an average along these finitely many points. Okay, so I'm being slightly annoying with some parenthetical comments here. So this is just to allude to the fact that ultimately you want to do this all quantitatively. But I'm not going to talk about quantitative aspects today. Okay, so if theta is rational, then I claim that averages of this nil sequence are sort of relatively easily analyzed. Okay, and the opposite situation is when theta is irrational, and it's sort of standard theory that then this sequence is going to equidistribute on the torus, and so so the average, say, that we're interested in is approximately equal to the integral of the torus. So this is what equidistribution means. So it's the it's precisely the statement on the slide. Okay, so I mean, in the example that we're given above, any theta is either rational or irrational. So so these are the precise two possibilities. Okay, so what about the sequence on the slide in R squared 1Z squared? So well, it's confined to a subgroup, so it certainly doesn't equidistribute on the whole thing, and it also certainly doesn't take finitely many points. So one has to allow for the possibility that you get equidistribution in a subgroup. So this is going to equidistribute in a diagonal subgroup. Okay, and finally, this is not the only phenomenon. So if you look at the sequence written on the slide, well, if you foliate into arithmetic progressions mod 3, you're either going to equidistribute in the same diagonal subgroup as before, or cosets of that. Okay, and in generality, these are sort of the only behaviors that you expect for sort of all polynomial sequences on nil manifolds. Okay. Okay, so a very useful theorem, which qualitatively is due to Liebman and then quantitatively due to Green Tao, is that we have equidistribution of a polynomial sequence on a nil manifold if and only if it doesn't sort of not equidistribute for a sort of trivial algebraic reason. So the trivial algebraic reason is that it lies in the kernel of some character, or is not sort of mapped to a constant by some character. Okay, as an upshot, you can iterate this quite easily to obtain a factorization result for arbitrary polynomial sequences on nil manifolds as the product of something which does indeed equidistribute in some subnil manifold and some rational sequence which will determine how it jumps between different cosets. Okay, and this is the stupid decomposition for our stupid example. Okay, so to study this average, the strategy is to, say, factorize like this, and then foliate into cosets, and then we can integrate over cosets on which we equidistribute. Okay, but to bring it back to sort of the original context of studying these T operators, we want we want averages evaluated at linear forms, at sequences of linear forms, rather than just the trivial linear form. So okay, so what do we do? So okay, so let's view this product as a multi-parameter nil sequence on the product nil manifold. So yeah, so the product polynomial sequence is just the polynomial sequence in each component evaluated at each set of linear forms, and the automorphic function is just the, I guess, tensor power of the original automorphic function. Okay, and by the multi-parameter version of the Green Tao theorem, you can, you know that this equidistributes in cosets of some subnil manifold of g to the t mod gamma to the t. Okay, and then so the arithmetic regularity lemma lets us reduce the analysis of nil sequences, and then as a consequence of this result, we can foliate into subprogressions and then look at a more algebraic problem of integrating over some coset of some nil manifold. Okay, so the goal here is, yeah, so I guess the local goal is given a polynomial sequence G and a set of linear forms to describe what the orbit is. So describe the subprogressions and then also describe the sort of connected nil manifold in which you do genuinely obtain equidistribution. Okay, so that's like the sort of local problem. If I'm handed a G and a psi, describe for that G and psi where we get equidistribution. But the sort of broader question is, in light of how this is used in sort of the arithmetic regularity lemma, if you want to study some property of these linear forms, you generally want to study this sort of uniformly over the space of nil sequences. And so the broader question, I guess, is to obtain structural information on sort of what this nil manifold can look like, sort of uniformly in all nil sequences, say bounded of fixed degree or something. Okay. Okay. Okay, cool. Okay, so one situation in which, okay, so one situation in which we can do this is when the linear forms satisfy a particular algebraic condition. So let's take our 4-term arithmetic progressions, and I'm going to write them slightly obtusely as this 1, 1, 1, 1 coefficient times x plus 0, 1, 2, 3 times d. I'm going to define my vector space V as just, I guess it's just the image of psi. Okay, and I'm going to define V squared as the square of V in the sense of taking coordinate-wise products. So yeah, so V squared is the smallest vector space which contains squares from V, and equivalently it's spanned by just the pairwise products of the things that of a basis for V. Okay, and in this example, V is contained in V squared. So this is coming from the fact that V contains this all ones vector. Okay, and the general definition is if you have nesting in this way. So a system of linear forms is flag. We'll say that a system of linear forms is flag if you have V contained in V squared, contained in V cubed, etc. So eventually this will stabilize and just be all of R to the T. But yeah, this is sort of the algebraic property that we're interested in. Okay, let me also remind you what a filtration is. So a filtration is a sequence of nested subgroups which satisfy this commutator relation. So the commutator of Gi and Gj is contained in Gi plus J.
So is anything that's translation invariant flag?
Exactly, yeah. But it's not an if and only if. Okay, so Green and Tao have the following theorem, which sort of answers the question from the previous slide. So if psi is flag and G is irrational with respect to a filtration, so I'll say a little bit about that in a moment. But if G satisfies some property with respect to a filtration, then we can describe the orbit of G to the psi explicitly in terms of the filtration and the set of linear forms. And indeed, the group that it the nil manifold that it equidistributes on is this Liebman group. So you just get the group generated by GI, and then, okay, this is potentially not the nicest notation, but what I mean by this is the vector of, say, of t things, where you go GI to the first coordinate of VI, GI to the second coordinate of VI, and so forth. Okay. Okay. Okay, so what does it mean to be irrational with respect to a filtration? I'm not going to go into full details about that, but I'll say a couple of words. So, okay, so firstly, you want G to be irrational in some way. So you don't want it to be like just 1/3, because then you're not going to get equidistribution in a connected thing. Okay, so if G is suitably irrational, then okay, so what is the data associated to G? It's a sequence of coefficients, G1, G2, so G1 to the n, G2 to the n squared, G3 to the n cubed, and so forth. Yeah, so a priori, if you want to know where G equidistributes, you need to know some data, some information about these coefficients. And okay, so the first guess at determining where this whole thing might equidistribute is to say, okay, well, the linear coefficient is going to, okay, so yeah, so the linear coefficient is going to so okay, let me draw a picture maybe. Okay, so let's say we're in the situation of having okay, so we've got a product of two manifolds, and let's just say G is just on some direct product of two things. We've got our linear part just living on one of them. We've got our quadratic part living on the other. Okay, so what values is this going to take when we compose with our system of linear forms? So we plug in our system of linear forms. We're certainly going to get everything in G1, well, to the V, because yeah, when we plug in psi here, the image of psi takes values in V. And here we're going to get everything in G2 to the V squared. Okay, so okay, so maybe an initial guess at a Liebman group would be something like G prime to the V and G prime prime to the V squared. Okay, so if G1 equidistributes in G and G2 equidistributes in, sorry, if G1 equidistributes in G prime and G2 equidistributes in G prime prime, then when we compose with this system of linear forms, this maybe is the initial sort of guess that we would have of where this thing might take values and where this thing might equidistribute. But Green and Tao observe that, yeah, so, okay, so what we want to do is we want to go from, we want to glean more structural information. So this may be true, but what we want to do is we want to, yeah, so okay, so Green and Tao observe that, so if our system is flagged, so if V squared contains V, then okay, then we might as well extend G prime. So yeah, so then we get everything in G prime prime to the V for free, just because yeah, just literally by that containment. Okay, so
before you go on, can you explain V square, how you define V square again?
So V squared is, you can define it in a couple of ways. So, okay, so one way to define it is literally just to take psi of xd, square it coordinate-wise, and look at the span of those things.
Okay, so that's it.
Okay. Okay. So yeah. So a priori, you might just your initial guess at a Liebman group.
Give it a second.
Okay. So our initial guess at a Liebman group might just be to say, where does our linear coefficient equidistribute? Okay, and let's take that to the sequence of vectors that we're gonna get in the exponent. Where does our quadratic thing equidistribute? Let's just take that to the so have that along vectors that we're going to get in the quadratic component. But I guess Green and Tao sort of do some data compression and observe that if we have this nesting of vector spaces, then in actual fact, the stuff in G to the T that we're going to get, which has sort of linear configuration V, is going to be, it's going to be not only the stuff in G prime, but you're also going to get the stuff in G prime prime just because of the this nesting. Okay, so that way we extend, or I guess Green and Tau extend from just an arbitrary sequence of subgroups to a sequence of nested subgroups, and then you can do a similar thing with just observing some identity about commutators to show that in actual fact you're gonna get you're automatically going to fill out this bigger structure than just the minimal nesting. Okay. So what irrational with respect to a filtration loosely means is that G is irrational in some certain sense. Each of its coefficients are irrational in some certain sense, and that this filtration is sort of the smallest one that contains G. It's a minimal filtration for containing G. And yeah, so yeah, okay. Okay, so what Green and Tau gain here is rather than just describing the equidistribution in terms of the individual subgroups on which each of the coefficients equidistribute, they get sort of more algebraic structure in terms of the sorts of things that we can see in the group on which the ultimate polynomial sequence equidistributes, and sort of as a result, one can sort of glean more structural information about the sorts of averages that we're interested in. Okay, and so such an equidistributional result is only useful if you can reduce an arbitrary polynomial sequence to something that satisfies this notion of irrationality. So at the end of the in the arithmetic regularity lemma, you're handed an arbitrary nil sequence. You're not handed one which satisfies whatever this notion of irrationality actually is. But the point is that an arbitrary nil sequence or an arbitrary polynomial sequence on a nil manifold can be reduced to the product of something which is rational and the product of something which is irrational with respect to filtration in the sense of Green and Tau.
Can you say a few more words? So what do you exactly mean? Maybe with an example. Irrational, irrational.
Okay, so irrational is okay, so I mean the actual definition is sort of technical.
Analog, you know, there are a few different definitions of the rationality which extend. For example, denseness of some orbits.
So irrationality is a sort of it's a finer property than equidistribution of the coefficients. So irrationality of some sequence is a statement about some properties of its coefficients. And this statement of irrationality on its coefficients is a finer property than just asking about where it equidistributes, where each of the coefficients are
In which respect finer, it's faster uniform distribution or more quantitative? Or...
Oh, so what is the difference? So I think, yeah, so so each Taylor coefficient, or each coefficient you want to so you take G1, I don't know if there's a
different look later. It's still just to feel better, especially since you say it's final notion. It would be nice to have a feel. Now your G.
Sorry, okay, so I should say, sorry, it's not, okay, so the condition on G being irrational is a finer notion than G equidistributing somewhere. But yeah, for each coefficient, so for each coefficient, it's less information than knowing exactly where the coefficient equidistributes. So you want to know where the coefficient equidistributes modulo, okay, so let's take the quadratic coefficient. You want to know where that equidistributes mod, so you care about where that equidistributes mod G3 and mod the group generated by G3 and commutators of degree 2.
Maybe that's what I wanted to ask. So G dot in theorem of Green Tao. What is G dot? Is it your?
Oh, sorry, I haven't. Okay, yeah, it's the sequence of
So I think
the
of
filtration.
G above it as G dot.
Yeah. Sorry, I should have said that. Yeah.
In this rationality, since it's with respect to filtration, it should keep being irrational with respect to its stages. Is that the field that I should create?
What do you mean by its stages?
Well, it's a sequence, right?
This is what I think one way to think about it is if I just write down my little G, split it into a Taylor sequence, a Taylor series of the coefficients, those are now just real numbers. Taking, you can write in coordinates so that these are real numbers, and you want some sort of irrationality condition on those real numbers, which will imply something about the equidistribution, but not vice versa, right? Is that the way that if there were rational dependence between these numbers, that might be bad in some certain sense, depending on the filtration. And we're saying that there are no rational dependencies between that.
Okay, please keep going.
So maybe the final sentence that I'll say about this is that, so G being irrational certainly implies that it equidistributes as a single valued, as a single variable sequence, but you need more information about it to determine its distribution when composed with a set of linear forms. And that information comes in the form of looking at sort of various rationality properties of each of the sequence of coefficients. So what it means to be rational or irrational. Okay, so let's look at a non-flag example. So it transpires that this flag condition, or if your system of linear forms is not flagged, then you don't necessarily equidistribute on the Liebman manifold. So first, for that sentence to have any content, I should convince you that there exists a system of linear forms which is non-flagged. Okay, so this is a system of linear forms. V is spanned by the original two vectors as usual. And V squared is spanned by their pairwise product. And V cubed is R to the 4. And in particular, you can verify, okay, that you don't have the containment of V and V squared. Okay. Okay, so let's look at this sequence on the Heisenberg group. So this is just an arbitrary linear sequence on the Heisenberg group. Okay, so one checks that the Liebman group is the stuff generated by the whole group to the V times, say, G2 is just the commutator subgroup, which is just the stuff with zeros in the A and B coordinate to the V squared. So this group is going to have, so in the A's and B's coordinate, you're going to have linear constraints corresponding to V. But in the top right coordinate, you're going to have all of R to the 4. So that's what this group looks like. It's a subgroup of G to the 4. Okay. Okay, so my claim is that even if you know exactly where this coefficient equidistributes, so even if you know where G1 equidistributes, you don't necessarily know where G to the psi equidistributes. That is when you compose with a system of linear forms. Okay, so you're going to have to take my word for some of this stuff. But okay, so I've defined the Liebman group. If this was flag, we would get equidistribution of G psi in the Liebman group. Now I'm going to identify a character on the Liebman group and show that, in fact, our polynomial sequence can lie in the kernel of this character and therefore not equidistribute on the full thing. Okay.
Excuse me, can you explain in V square, the line 4? Yeah. I understand the first two vectors, and how the third one comes about.
So it's the pair. So you get it comes from all pairwise products of basis vectors of V. So it's this vector times this vector. Yeah. So V squared is just the smallest.
Okay, I got it.
Yeah. So in particular, V squared is the vector space that. So if you have the polynomial sequence n squared and you compose this with your set of linear forms, you get psi squared, and then psi squared takes values in V squared. So that's okay. 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 So I'm going to identify for you a character. So my character is going to take a sequence of 4 elements of the Heisenberg group and take sort of the following inner product with the sequence of top right coordinates. So you take their sequence of top right coordinates. I'm going to take this vector W and take their dot product, and it transpires that this eta is a character on this group. And this uses crucially the fact that this uses crucially the fact that W lies in the perp of V squared. So okay. So if eta is a non-trivial character on my Liebman group, and our polynomial sequence lies in its kernel, then we don't get equidistribution on the full Liebman group. Okay, so for this eta to be interesting, we need it to indeed be non-trivial on the Liebman group, and this is where we're sort of using the fact that these things are non-flag. So yeah. Okay, so then one computes eta composed with this polynomial sequence.
Sorry, you said we're using here that it's on flag. Is the point that W is somehow in V, or?
Yeah, so the point is that W is in the perp of V squared, but it's not in the perp of V. Okay, so yeah, so we compose with this polynomial sequence, and yeah, so the resulting polynomial sequence that you get in just R mod Z is it's just this thing as a polynomial in X and Y. The point is you don't get any quadratic stuff because because W is constructed to lie in V squared perp. But this is not the zero polynomial sequence because W does not lie in V perp. So this is where we're using the non-flagness. So this sequence is non-constant and therefore equidistributes unless C is equal to a half AB. So if we constructed our initial polynomial sequence to have C being a half AB, then indeed, G to the psi lies in the kernel of eta, and so it's not going to equidistribute in the full Liebman group because it lies in some codimension 1 subgroup. Okay, and so an arbitrary G1, which is just coordinates ABC, and the special G1 where C is equal to a half AB, both of these two things equidistribute in the same places as univariate polynomial sequences. So ultimately, even the distribution of the individual coefficients of our polynomial sequence is not enough to determine the distribution of G to the psi in the non-flag setting and in sort of the smallest non-abelian case. It is actually true in the abelian case, but it's not true in sort of the smallest non-abelian case. Okay, so the question is then, if we want to get this arithmetic regularity lemma strategy to work, what data from a polynomial sequence G determines the distribution of G when composed with a system of linear forms? if not the distribution of each of its individual coefficients.
When you, should ask as well though, when you say the individual coefficients of the polynomial sequence, do you mean the coefficients when you take the Taylor expansion or the?
Yeah, I mean, it's equivalent, but certainly any polynomial sequence can be written in this form. So, I mean, if you want to use like n choose 2 or something, that's fine. But
Okay, and do you want you to take the coefficients? Then?
yeah, sorry, the coefficients. Gotcha. So the data to a polynomial sequence is this sequence of coefficients, and yeah, if you want to know, so when you compose this with psi, you want to know where G psi equidistributes, and the question is, how can you do that from data of this polynomial sequence? Yeah, so in this case, we just have a linear, this is a linear sequence, we just have a G1, and our G1 is this sort of Heisenberg matrix. Okay, and the answer transpires that, so it's not enough to understand where these individual coefficients equidistribute in the Lie group, but it transpires that if you look at the distribution in the Lie algebra, additively at least. So in the Lie algebra, you have an additive operation. I guess you've got a Lie bracket, you've got a group action as well, which comes from the Lie group. But if you look at the additive distribution in the Lie algebra, it transpires that now this is enough. So again,
Sorry, and I should predict this because C minus the half AB is precisely telling me when the central coordinate of the algebra is 0 or something.
Yeah. So in this case, exactly. I mean, that's exactly where it's coming from. Yeah. Okay. So we're going to move to the Lie algebra. Okay. So now I have some abstract stuff to throw at you. Okay. So we want to interpret this example and the theory in general in the Lie algebra. So the situation is, so I hope you agree with this fact. If we have some sublattice of a lattice of finite index, then a polynomial sequence will equidistribute on the quotient with respect to the smaller group if and only if it equidistributes in the quotient with respect to the larger lattice. So this is just by like covering your quotient with like finitely many cosets or something. Okay, so let me throw this definition at you. We'll say that two lattices are commensurable if their intersection has finite index in both. Okay, so we extend the above observation then to observe that if two lattices are commensurable, we get equidistribution of a polynomial sequence with respect to one if and only if the other by passing to the intersection. Okay, and it transpires that the commensurability of lattices has a nice interpretation in Lie algebra. So it transpires that if you've got some lattice in the Lie group, you take log of that and interpret that as a set in the Lie algebra, and you take its Q linear span, then two lattices are commensurable in the Lie group if and only if this Q linear span in the Lie algebra is equal. Okay, I've got one more definition to throw at you. So a rational structure for a Lie algebra, for a real Lie algebra, is a rational Lie algebra, rational Lie subalgebra, which is full dimension as when you take its R span. So I mean, just think of like Q to the n and R to the n if you don't like this definition. Okay, and you can pass between these two worlds. So for any rational structure, G, Q, and G, it is indeed true that there is a lattice in the group who's such that when you pass to Lie algebra and take its Q span, you get the original rational structure that you started with. And conversely, for any lattice in the Lie group, the Q span of its image in the Lie algebra is a rational structure. Okay, so lattices in the Lie group are essentially the same thing as rational structures in the Lie algebra. And furthermore, by the fact above, we can pass not only to lattices in the Lie group, but we can look at commensurability classes of lattices in the Lie group. So two commensurable lattices in the Lie group will determine the same rational structure in the Lie algebra. Okay, and as a result of this, we can interpret equidistribution not with respect to sort of one lattice at a time, but with respect to a commensurability class of lattices, and therefore with respect to a rational structure. Okay, so all of this being said, we can interpret equidistribution in the Lie algebra. So a polynomial sequence equidistributes in the Lie algebra with respect to a rational structure if the corresponding thing equidistributes in the Lie group with respect to a lattice. And so a priori, this is not at all well defined, but by the facts that I've thrown at you on the slide, this is well defined. Okay, so if you want to bring this back down to earth, so the observation is that, yeah, you equidistribute in R mod Z if and only if you equidistribute in like R mod 2Z, like a polynomial sequence, or equidistribute in Z if and only if it equidistributes in R mod 2Z, or indeed any rational multiple of Z. And so I can define equidistribution with respect to R mod Q just by taking any element of Q and multiplying by Z. So that's the abelian version, and this works in generality in the non-abelian case. Okay, and then one can lift the Liebman-Green Tao stuff to the Lie algebra. And the condition that you get is you get equidistribution with respect to a rational structure. So yeah, so the rational structure that we're using here is implicitly Q. Another irrational structure that you might use is like Q square root 2 or some other Q vector subspace. But okay, so we get equidistribution in the Lie algebra with respect to a rational structure if and only if for every non-trivial rational Lie algebra homomorphism, when you compose the polynomial sequence with this homomorphism, you don't take values in Q. So this is sort of the infinitary sort of linear version interpreted under all of this theory of what you get in the Lie algebra when you try to translate what the original Liebman-Green Tao theorem was.
Sorry, what's Lie algebra homomorphism?
So it's a Lie group homomorphism that respects the Lie bracket. So so a Lie algebra homomorphism to R is just something that vanishes on the commutator subalgebra. But so yeah, you've got a Lie algebra homomorphism to an abelian thing, so it had better vanish on commutators, and that's all. So it's just it's a vector space map. It's a linear map which vanishes on commutators.
And so by rational Lie algebra homomorphism, you mean one that it's specified by rational numbers?
Basically, yeah. So the abstract definition is one that maps the rational structure to Q. Yeah. Okay. Okay, so given any polynomial sequence in the Lie group, we can interpret it as a polynomial sequence of this form in the Lie algebra. And we have some fixed linear pattern, and we want to know by our previous definition where this polynomial sequence composed with a set of linear forms distributes in the Lie algebra. Okay, so a priori this takes values in our Lie algebra to the t, so g to the t. For technical reasons, it's easier to view this as just g tensor r to the t. So the point is that all of the information coming from our system of linear forms all of that is going to happen in the r to the t component, and all of the stuff to do with the rationality of our polynomial sequence is going to happen in the g part. So this is certainly true as a vector space isomorphism under this map, and g tensor r to the t inherits a Lie bracket operation just from the Lie bracket that you get on g to the t. Okay, so now I can sort of answer literally your question from earlier in generality in the non-flag setting. Okay, so we'll say that, okay, so we're not looking at polynomial sequences now. We're looking at elements of the Lie algebra. So an element of the Lie algebra is linearly irrational with respect to a rational structure if for all rational linear maps, so all maps which map that rational structure to Q, So if you're in like R to the n and your rational structure is q to the n, then these are just q, the thing that you would expect. So if we're all rational linear maps, we have the property that if indeed that linear map maps your element to q, then in fact your element lies in the kernel of that linear map. So this is somehow detecting that the orbit of this element of the Lie algebra is going to equidistribute in some connected subspace. So if it's the case that if it's not the case that this thing is 0 and elevate takes some rational value which is non-zero, then you're going to get equidistribution not in a connected subalgebra. Okay, so this is the notion of irrationality for elements of the Lie algebra, and we'll say that a polynomial sequence is linearly irrational just if all of its coefficients satisfy this condition. Okay, so here's the theorem. So a polynomial sequence. Okay, so a polynomial sequence which is linearly irrational in the sense that each coefficient is linearly irrational by the definition above, will indeed equidistribute in a connected Lie subalgebra, and it's the one written on the slide. So it's the smallest Lie subalgebra generated by generated by the tensors on the slide. So
you have erasers here, many.
Oh, okay. Yeah, okay. So
And this is your theorem.
yeah, but so I mean ultimately, yeah, so ultimately one wants to do this all quantitatively. And but yeah, this is sort of the qualitative version which sort of sees the algebra of what's going on. Okay, so just to compare with the flag version, so in the flag version, we had the polynomial sequence, which was suitably irrational with respect to a filtration. So this equidistributed, so sorry, when you compose it with a set of linear forms, this equidistributes in the Liebman group, which was just vi to the v to the I. Okay, and so we argued before with our Heisenberg example that doesn't happen in the Lie group, with non-flag patterns. But it transpires that the analogous thing of looking at, so this SI, the smallest rational subspace containing A, is precisely where the orbit of A is gonna distribute additively in the Lie algebra. So you look at the distribution of AI additively in the Lie algebra, and you take its tensor with the appropriate vector space. And it transpires that this sort of does give the answer.
Before you go, could you think maybe you already said this, I just didn't get it. This thing of linearly irrational. What is it possible to give the most basic example of the Lie algebra where an element that is a linearly irrational, one that isn't?
Yeah. So okay. So let's look at this example from before. So our previous sequence. So we had this sequence, and then we had this. So okay. So my claim is that this is linearly irrational. This is not, just because. So this lies in the kernel of. Okay. So any rational linear combination of these two things that you take that lies in Q is in fact going to lie in 0. Is in fact just going to be 0. Whereas that is not true for this. So if you take 1 minus 1 dot product with 2. So this thing is what, like minus a third or something. So yeah, this is detecting precisely the distinction between these two things.
Okay. And somehow that second example is bad for computing the Leibniz submanifold.
Yeah, so well, it's
Because it would be non-equidistributed, as it has these different non-equidistributed components.
exactly, it's going to equidistribute in cosets. So this equidistributes in cosets. It's not in a connected thing.
So your pre-processing on your manifold would say, in that case, dump all but one of the cosets and look at that, and then apply this thing.
Yeah, so the pre-processing is to factorize the polynomial sequence. So my claim is that I can factorize any polynomial sequence to something which is linearly irrational times something which is periodic. And then I do the same thing as well.
Okay. So I should think of linear irrational as meaning equidistributes possibly over some subnull manifold,
But a connected
but
one.
not worse than that. Okay.
Exactly. It equidistributes in a connected space. Okay, I was going to prove it for you. We probably won't have time to do that, but the full proof is 9 lines. So don't read the proof, but what I want you to appreciate is that, okay, so firstly, the Liebman-Green Tao result reduces a distributional question to what is essentially an algebraic question. You're looking at whether sequences lie in the kernel of characters. And this observation about the commensurability of different lattices means that basically you reduce what is an algebraic question to what is a linearly algebraic question. And the proof is essentially linear algebra, suitably interpreted. I mean, yeah. Once you set up stuff right, it's really not so bad. Okay, and this is the thing that Freddie was asking about. So yeah, there's no point in having some really stringent condition which determines the equidistribution of a polynomial sequence if you can't reduce a general polynomial sequence to something that satisfies that condition. And so this theorem says that, yeah, indeed you can reduce a general polynomial sequence to the product of something which is periodic and the product of something which does satisfy this linear irrationality condition. Okay, I'll stop there, thanks.
Can I ask one? So in the non-flag example, the simple one that you gave us there, it's now easy to go and compute the analogous Leibman group.
Yeah. So okay. I mean, I can do this. I can do it in 2 minutes, 1 minute. Yeah. So the point is that, yeah. So okay, so this is the polynomial sequence in the Lie group. When you take the logarithm map, the thing that you're going to get in the Lie algebra is just AB. So the Lie algebra is a 3-dimensional thing. I think the map is like, so the log map maps this to things like C minus a half AB or something. Okay, so you've got 3 coordinates in the Lie algebra, and our example where we take, so the bad case was where we took C to be a half AB. And the point is that its third coordinate in the Lie algebra is going to be 0. And so additively, this distributes on a smaller subspace in the Lie algebra than what an arbitrary thing does if this was just C minus a half AB. So generically in the Lie algebra, if these are just 3 like irrational, non-rationally dependent things, additively it's going to distribute on R cubed. But the Lie algebra sees that actually the top coordinate is 0, and so additively it's going to distribute on something smaller, and then this these through. Yeah.
So that wouldn't affect distribution in G mod gamma. Is that right? The third coordinate isn't important, but once you sort of product it up, then it becomes important. Is that
so once you compose with the linear maps. So that's
yeah, right.
Exactly.
So without the phi, it doesn't affect the equidistribution. You're sort of
exactly. So this is like the main like counterintuitive thing, I think, is that, yeah, so without composing with phi, regardless of what this top coordinate is, a half AB or not, the sequence like G1 to the N is going to distribute in the same thing. But when you compose with the phi, somehow it matters what this top coordinate is, and you can only really see that in the Lie algebra. Or some coordinates, yeah. So yeah.
So if we're trying to find the central crime of the original Green Tao argument, which led to this flag condition that shouldn't be there, I mean, so I think does this make sense? So when you take the Taylor series in the group setting, and that's like a sort of poor man's Baker-Campbell-Hausdorff formula or something, right? That you're sort of
So just think about the abelian example, because I mean, you could the flag and non-flag thing, like you still need it's still a necessary distinction even in the abelian setting. So don't worry about Baker-Campbell-Hausdorff.
oh, okay.
So I think that the main example, which I sort of described relatively poorly earlier on, is if you just take the product of say two toruses, and so this is going to be like G2 n squared, and this is like G1 to the n. So when you compose this with your linear system, so the linear part is gonna, okay, so when you compose it with your linear system, you get t copies of whatever this manifold is, right? But the linear sequence is only gonna sort of take values in this half, and the quadratic sequence is only gonna take values in this half. And so certainly, okay, so this is fine. So you're gonna get like G1 to the V and G2 to the V squared when you compose with your linear system. But ultimately, so the question is, what is your filtration here? So Green and Tao insist that the filtration has G1 containing G2, right? So what is your filtration? So the only filtration that you can do here is if little G1 equidistributes here and G2 equidistributes here, then G1 had better be the whole thing, right? Because it contains where little G1 equidistributes, and it has to contain G2, right? And so, so this nesting, the nesting condition is you can't reduce to, you can't reduce to sequences of groups that are necessarily nested, because so it's fine. Yeah. So the question is, how do you define your G1? My claim is that if it's going to satisfy a filtration, then G1 has to be the full thing. But then the Liebman group is G1 to the V, and if V squared doesn't know anything about V, then you're not going to get like G1 to the V vectors on this side. I mean, there are examples written down like in my paper on Terry's blog, which maybe sort of spell this out with sort of less anxiously.
Okay, yes.
Can you say a bit about like applications, or like which things were broken by like the original, like the Green Tao thing, like being wrong? Like what does this fix?
So the main thing that sort of fell through as a result of the Green Tao stuff working for flag stuff is that so you wanted this conjecture of Gauss-Wolff, which asks for which norm that you want to control your what is the best Gauss norm that controls your system of linear patterns. So previously this was only answered for flag systems of linear forms, but using this machinery you can go through and resolve the whole thing. It's sort of so one thing that I should say is that you necessarily get less sort of structural information about the nil manifold that you equidistribute on, right? I mean, you've got less information to start with, but you have less structural information about the thing that you equidistribute on at the end. And so for applications, you may have to do a little bit more work in any one direction depending on what sort of structural properties you want that Lie group or Lie algebra to have. So yeah, so I do a little bit of this in my paper for this particular Gauss-Wolff problem, but it's sort of unclear to me without another application handed to me, sort of what extra sort of structural work one might have to do, like algebraic work in the Lie algebra one might have to do, and yeah, so how much you sort of structurally lose out.
Any more questions?
So I have a open-ended question, but so you deal with linear forms. Is there any hope to extend this to polynomial forms?
Yeah. So okay. So the proof, which I didn't show you, goes through almost line for line for a certain set of linear forms. So it goes through for a certain set of polynomial forms. So this, the constraint is essentially that you don't want your polynomial forms having different degrees interfering with each other. So it would work for say something like, I don't know. So it would work for something like that, for that sort of polynomial pattern, but it wouldn't work for something like, okay, so naively it wouldn't work for something like this, because, so the condition is that you don't want some polynomial in one of your forms to have terms which appear in other of your forms of distinct degrees. So when you square this middle form, you're going to get a y squared, and then that's going to interact with the y squared from over here. Okay, but if you have a sequence of polynomials such that all univariate polynomials in each of these coordinates, you're not going to get overlapping terms from distinct degree polynomials, then the proof goes through line by line.
So if you replace the last line by x plus y squared, x plus 2y squared, it's equally bad.
Yes. So yeah, so okay, so I mean, this is something that I've been meaning to think about for a while. I suspect that there are ways to get around this, but yeah, line by line, yeah, like polynomial progressions are a perfect example of something for which this is going to fail, because yeah, precisely because when you have different degree contributions from different linear forms.
So for the polynomial progressions for which this does work, then can you like just say what their true complexity is? Like, is this enough?
You should be able to, yeah. I haven't written it down.
But
yeah,
it will be a relatively special class. And not surprising, it's very complicated. This.
I think, yeah. So certainly, if you're looking at polynomial progressions or in two variables, then like you say, you're almost certainly going to have something of this form. However, so I mean, a nice easy example for which it does work is if you like look at like any sort of multiplicative pattern. So anything which comes from like a multiplicative Gauss norm or something like that. So anything like that is any higher order polynomial in any one of these is not going to have a term which overlaps from another one. And so I can tell you, yeah, so it works.
You can say what about those?
I can say where that distributes.
I see. So it's not true that if you take that configuration that you can get global control by any Gauss norm, because it's not.
No, I'm not claiming control.
But it's something.
I'm saying that if you have an additive nil sequence,
yeah, I see.
Evaluated at these patterns.
Right.
Yeah, I mean,
if a priori, you know, there's an additive nil sequence.
Exactly. Yeah, no, I'm definitely not. Otherwise, it would be a very false claim. But yeah, so if you do know that something is controlled by an additive Gauss norm, and in the first instance, if it satisfies this condition, then I should be able to tell you its complexity, like what its true additive complexity is. Maybe there's, yeah, I should give thought. Maybe this talk will be the impetus for me to write this down and see if I can use any tricks to broaden that class. But yeah, certainly it doesn't tell you when you can get controlled by an additive Gauss norm.
There are no more questions. Let's thank Dan again.